Okay, pyrimidine catabolism. So pyrimidine catabolism is relatively straightforward, but it provides the answer to a mystery that's been nagging us since we talked about the branched chain amino acid catabolism, particularly the valine catabolism. Remember, we had a bunch of problems, and then we found some solutions. And then we had one kind of goofy little thing that didn't make any sense on valine. You remember what that is? You should know what this is right now. What is the really stupid thing about valine catabolism? So far, it makes no sense. You just have to memorize it. And, I know some people want to memorize things, but I don't memorize anything. I like to understand things. And if I can't understand something, it nags at me. That's why I'm a scientist, I guess. Okay, so we're going to start here, and just like purine catabolism, okay, so here I'm going to draw them in this orientation just as we made when we synthesize them, which is kind of the backwards way that we normally draw them in the anti-orientation of a Haworth projection, because that's how we made them. And, just like we needed to put energy in going up, right? Going up, what we did from this is we went Q to E, and we used ATP, right? That's going up in biosynthesis. Going down, of course, if it requires energy to go up, it must be favorable to go down. So I could just hydrolyze off this and NH3. And I get to urea. So, and once again, we remove all the riboses. So we're just talking about catabolism of the bases now. Okay? They get removed, and you get ribose 5-phosphate, which feeds into the pentose phosphate pathway and can be completely metabolized in that fashion, or can be converted by other things. Okay, so just like purine catabolism, what we need to do is we need to break this bond, and this is stabilized because this is an aromatic system. So if we can just make it not aromatic, all we need to do, if we can make this not aromatic right here, there we go. And if I can reduce this bond, and I'm going to reduce it with, here's my blue pen, here we go. I'm going to reduce it with N, and once I've reduced it, fantastic. I get this dihydrouracil. What am I doing? I reduce it. Okay. And this is now not an aromatic system. It's just a regular amide, and I could hydrolyze theoretically either one of those two. And the enzyme, what we do is we choose to metabolize this one. Okay. So when we hydrolyze that, we break open the amide, and we get this thing. Oh, sorry. Break open the amide, so we get that thing. We get the carboxylic acid and the amine. And this kind of looks like urea, but you have to pay attention here. Okay? Here we have this amide. What we're going to do is we're going to bust this open here. Here's the amide that we're going to bust open. Right? So we're not going to get urea. We're going to get this carboxylic acid out. We hydrolyze it again. And what we're going to get is we're going to get this thing out. Acid and the amine. Okay? Not urea. Don't put urea, you're wrong. This is carbamate. Remember, we saw carbamate in the urea cycle where we produced carbonyl phosphate and we added ammonia and we got carbamate, and then we had to phosphorylate it to get carbamoyl phosphate. Of course, going backwards doesn't require energy, it's just a hydrolysis again, and we get carbonate, which equals CO2, and we get ammonia. Okay, and this gets either sucked up by the urea cycle in most terrestrial organisms, or it gets secreted by some aquatic organism, marine invertebrates mostly. Okay, so what we have here, we have an amino acid. Where have you seen this before? We actually saw this before. Have you ever seen this before? I don't know. I'm sure you've seen this before. Let's go to. I'm going to go way down here. How about this thing? Okay. CoA, beta alanine. CoA comes. This is where it comes from. Beta alanine. This is not a regular amino. This is amino acid beta. It comes in. It's in CoA. All right. So now you know part of the way of how to make CoA. But this being just an amino acid, what we do, of course, is we transaminate it, right, to dispose of the nitrogen if we're disposing of it into the urea cycle. So alpha ketoglutarate. E, and then we could say, well, this goes through the urea cycle and ends up in urea for secretion. There we go. And of course, this is going to have some cost, right? For one of these nitrogens, it cost us 2 A's, and it's going to generate an N. All right, there we go. And when we transaminate, I get this thing. Okay? All right, so what do I do with this? This is the end product, really. And here's where we have a little bit of a problem, okay? But I want you to consider one thing before we get to this problem, okay? What if I had T? I just did this two standard ones, RNA and C and U. You know, and that's RNA. We have more RNA in our body than DNA. But if we have DNA, this would be T, right? I would have a thing here, T, T, T. Then we get this thing. Now, does that provide you a solution? Okay, so we get two things. We either get this thing or we get the other, or we get from. Right, this comes from C and U, and this comes from T. Okay, so what do we do? Well, let's look at our valine problem. I'm going to come up here and get my valine problem. Valine. All right, so valine. Let's just review valine catabolism right here. Here's valine. We transaminate, and I'm not going to show all the different things. I'm just going to show the carbon, right? You have to know all the things. We did that in a different thing. And then we go to this CoA, and then we went to this thing, and then we went to this thing, right? That's valine catabolism with various things in there. Then we said, well, eventually we want to get down, but we do something goofy. We hydrolyze it to this alcohol. Okay? And then what we do is we oxidize it to this thing. Then we take this thing and we oxidize it again in a fashion that decarboxylates. Okay, and we get this thing on away. And then we finish the catabolism that comes all the way down. I could say, well, here we had isoleucine went all the way down to here, right? And then we finish the catabolism, CO2, ATP, and we get this thing. And then we rearrange it, and we get succinyl-CoA, which goes into the TCA cycle. Okay? And so we had to take anything, and we didn't make any sense. We said at the time, well, it would be very logical if I could just do this and oxidize this thing twice to come to here and get this thing. In essence, by taking this real branch, I spend this extra ATP in valine catabolism, right? Because I already have this pathway for leucine, for isoleucine, and clearly now I can see I already had this pathway for threonine. This shows that really this is primordial. The nucleotides came first because this was a pre-existing pathway, and the reason we can hydrolyze it is I don't need to make these two enzymes. I already have this enzyme here, okay? So because I already have this pathway, I can feed into the nucleotide pathway, and it solves this mystery. I'm just connecting, instead of spending effort to connect it down here, I connect it by a shorter path into the thymidine catabolism pathway, which creates this thing. Now, once we understand that, we can understand what we do with this. We do the same thing. In fact, I think it's the same enzyme. We decarboxylate in an oxidative fashion for C and U, right? CO2, and no, not red pen, blue pen, oxidative fashion, and in the same thing, instead of this thing left on here, we get, of course, acetyl-CoA. And of course, that also goes into the TCA cycle. There we go. Tyrosine catabolism, or not tyrosine, pyrimidine catabolism, and this mystery. Here, this is pyrimidine catabolism, and you shouldn't show any of this. You don't have to show any of this unless I ask you, well, how is valine and pyrimidine catabolism related? Or why in valine catabolism do we hydrolyze and then re-spend ATP to get back into a CoA? This is the reason, and this can help you remember these two pathways. Okay? All right, that's it.